This is number 36 from chapter 6.2 in the back of your book. Consider the following reaction. The CH4 in the gas form plus 2 O2s in the gas form react to form CO2 in the gas form and 2 H2Os also in the gas form with a delta H of negative 891 kilojoules per mole. Calculate the enthalpy change for each of the following cases. Now in this situation, I'd like to point out, I am not calculating how much energy is released. I am calculating the enthalpy change. I'm not saying it's being released or absorbed at all. I'm going to represent something with a delta H equals and a Kj. So, in order to communicate the direction, the exothermic or endothermic nature of the process, if it's exothermic, I'm going to include a negative there. If it's endothermic, there's going to be a positive. Okay, exothermic, there'll be a negative. Endothermic, make that number a positive. Start with A. 1.00 grams of methane is burned in excess oxygen. Now, we have this value here, this delta H, negative 891 kJ per mole. I'm going to use that to calculate here, but I don't have moles, so I'm going to convert 1.00 grams of methane, convert into moles of methane. Looking at your periodic table, you should be able to calculate that the molar mass of methane is 16.04 grams of methane. Now that this calculation will be in moles because the grams of methane will cancel, I can now use this term to calculate the enthalpy change here. Let's see, so I'll go negative 891 kJ per 1 mole of CH4. Now my moles of methane will cancel out. My unit will be in kJ, which is what I'm looking for here. And I need to remember that if this is an exothermic reaction, I need to include a negative sign, but if it's an endothermic reaction, I'm going to leave it positive. So using the calculator, 1 times 1 times negative 891, all divided by 16.04 times 1. We come up with negative 55.5 kilojoules. Again, this is enthalpy change, so in the language you're not saying absorbed or released, so your answer needs to include the direction of the energy flow. That's why when using the delta H term as a conversion factor, I included the negative sign to indicate that it is an exothermic reaction. That energy is moving from the system into the surroundings, so that as I did my calculation, that negative sign came through in the end. B. 1.00 times 10 to the third liters of methane gas at 470 torr and 25 degrees Celsius is burned in excess oxygen. Now, if I am going to use this value up here, I need to know how many moles are being combusted. Here I don't have how many moles are being combusted, but I have volume, I have pressure, and I have temperature. I hope these terms look somewhat familiar because they are the terms used in the ideal gas law. And so I have I have volume, I have pressure, and I have temperature. So I can plug all of these in to Pivnert and solve for N, which represents number of moles. And then I can use that molar value and the given enthalpy change per mole to calculate how much, the enthalpy change of this reaction. Now I'm going to do that, but I would like to point out that this 740 torr is not the type of unit that I need to use here. In PivNert, this P, this pressure, needs to be in atmosphere. So I'm going to take that 740, I'm going to bring that decimal so I know that all three of those numbers are significant. 740 torr, convert it into atmospheres. Calculator, 740 divided by 760 is 0.97. And I'm going to use three significant figures, so that'll be 0.974 atmospheres. Also, this is in degrees Celsius. And I don't want that to be in degrees Celsius. I want that to be in Kelvin. So I'll take 25 degrees Celsius. I'll add 273, so that will become 298 Kelvin. Now all my units are going to be correct, so when I pump that in there, I'll have, let's see, first I'll solve for N. Make it a little easier on myself later on. So I'll end up solving for N is equal to RT divided by PV. So that will be, let's see, oh, I'm sorry, I did that kind of silly, just realized that, I knew it looked funny. It's going to be PV over RT, good thing I'm crazy. Alright, so I'll take my 0.974, multiply that by my volume, which is 1.00 times 10 to the third. And I'll divide by 0.08206 and 298 Kelvin. Using my calculator skills, and see, I'm going to use three significant figures here. You got 3, 3, 3, 4. So I'm going to use three significant figures, so that'll make it 39.8 moles of methane. Now I will use this molar value of methane, 39.8 moles of methane. And now I can use my value from the question, the negative 891 kJ per mole. So again, this is an exothermic process, and I'm calculating enthalpy change. I'm not stating whether or not the energy is going in or out, being released or absorbed, so I have to relay that using this negative sign. That's an exothermic reaction. Again, this is per 1 mole of methane according to the equation up here, 1 mole of methane. So moles of methane will cancel. I'll have kJ left as my unit after I'm done calculating. The question is asking me to calculate the enthalpy change, so that is what I want. So I'll have a kJ. It'll end up being negative, which makes sense because this is combustion. It's being burned in excess oxygen, so that's an exothermic reaction. Energy is going from the system into the surroundings, so it makes sense that I would have a negative sign there. But doing some matemáticas, I'll end up with, let's see, I'm in kilojoules, So let's see, I got it's negative 35,461 joules. I'm going to turn that into kilojoules. So move 3, 5, and then I want 3 significant figures, so 5. I'll move that decimal right there. Nope, that's not right. That's not right at all. I'm sorry. Negative. That's 35,000 joules, so 35.5 kilojoules. Again, I don't have to say released or absorbed because I've included this negative sign right here.